when the electric power is transmitted from the generating stations over long distances. What did we do here? Here we used a step-up transformer to increase the level of the voltage level, right? So why we do this? Why we use high voltage for transmission? Why high voltage is required for transmission? With high voltage, the power losses are going to be less, will be reduced. So what is the power? The active power is what we want. So this is VI cos phi, right? V is the voltage at which transmission is happening. So for a particular power that is to be delivered, what will be I? I is equal to P by V cos phi. Okay, and now we can write the power losses. This is power losses and this is the active power that is transmitted. Okay, so what is the power loss? This is equal to I square into R, where R is the resistance of the transmission line. So instead of R, if you substitute this, then what you're going to get here? P square R divided by V square cos square phi. Here you can see that for a particular power and for a particular cos phi, what is going to happen? The voltage is going to decide how much power losses are going to be there. Higher the voltage, lesser will be the power losses, right? So for a particular power and power factor, that is cos phi, the losses is going to inversely depend on the voltage. Okay, so this means that higher voltage will result in lower losses. The next reason is the saving in the volume of conductor. Okay, so if you remember the resistance expression rho L by A. Now the power loss expression PL is equal to P square R by V square cos square phi, right? Here we have seen this is the power loss. Now if you substitute this value of R here, then what you are going to get? PL is equal to P square rho L by V square A cos square phi. From here you can get the area. This is equal to what? P square rho L divided by PL V square cos square phi, right? So you can see that for a particular value of the power to be transmitted, for particular losses and power factor, the area is inversely proportional to the voltage, right? For a particular value of the power loss and the power factor, you can write that area is proportional to 1 by V square, or you can say inversely proportional to the square of the voltage. Now what will happen when the area of cross section is more? It means that the volume of conductor is more, right? So volume of conductor, which is equal to the area of cross section into line length, right? So if area is inversely proportional to voltage, then volume is also proportional to, or inversely proportional to the voltage. Okay, so that means if you use a higher voltage, then the volume is going to reduce. Okay, so for a higher voltage, lesser volume is required for the transmission of given power. So these are the prominent reasons. One is that the line losses will be reduced and also the volume of conductor will be reduced. So volume of conductor is, if it is reduced, it means it is a more economical option. Okay, so this means it is more economical. Now if high voltage is so advantageous, then why not just, like, what is the upper limit? Because we cannot just keep increasing the voltage. So what is the limiting factor here? The limiting factor is the insulation cost. Higher the voltage, higher is the insulation cost, right? So insulation cost is the limiting factor. That is how we can set the upper limit for the voltage.